Computer graphics is easily the coolest thing that you can do with a computer. Graphics programming is the art of drawing something on the screen with programs. Your screen is your canvas, and your tool is a bunch of poorly written C++ code that is on the verge of hanging itself. Okay, so why would you use OpenGL when you can use something like Unity or Unreal or something like that? First of all, you'll learn a lot about the underlying principles, like the graphics pipeline and so on. Secondly, you avoid the bloat, which is always good. And thirdly, Aura. Okay, so what is OpenGL? OpenGL is a graphics API. It comes with a bunch of really useful tools that we'll be using throughout the course of this video. OpenGL basically allows us to talk with the GPU and do a bunch of graphics operations really easily. Okay, so how does OpenGL work? OpenGL is something called a state machine. So we call state using functions that use the machine as it is. We can change the state using certain state changing operations. A useful analogy would be to think of OpenGL as a driller, and we can use it as it is, or we can change the drill bit and then use it. The state changing operation involves changing a group of certain options. So we bind an object which contains a list of options that we want to change. Then we call it, then we unbind it. This is how we change the state of the machine. Here's an example. We create an object, then we bind it to the window changing option, then we call it, and then we unbind it. This is a common workflow in OpenGL. Okay, but how do we actually draw something on the screen? Basically, we have something called the graphics pipeline, through which we send in individual vertices, and the output is an image on the screen. This involves several steps. The first step is the vertex shader. The vertex shader converts the vertices we provide into a form that can be easily mapped to the screen. The rasterizer actually maps those vertices to the pixels on the screen, and the fragment shader colors those pixels. Textures are also a form of coloring if you really think about it. So that is also done on the fragment shader layer. Okay, so how does this look in practice? Let's say I want to make a spinning cube with shaman on it, because why the fuck not? First, we create a window with the help of the glfw library. We declare the width and height and so forth. Next, we create an array containing a list of all the vertices. Now, here's a fun fact about the OpenGL graphics. Basically, in OpenGL, everything is in terms of triangles. So, using two triangles, we can make a square, and with six squares, we can make a cube. So we just declare the position of each vertex of each triangle directly, and we just assemble them together to make a cube. Simple as that. Now, another set of coordinates are used to declare where the texture starts and where it ends. We use the vertex attribute pointer to tell the GPU how our data is structured. So as we pass the data, it knows how to read it and where to look for the position values and where to look for the texture coordinates. Think of it like a manual of sorts. Next, we load in the textures using the STB image library, which makes things really easy for us. Okay, now we can pass the data to the shader. Let's take a look at the shaders. The vertex shader has location is equal to 0 and to designate the position, and location is equal to 1 to designate the texture data. Now the model and view and projection variables are matrices that transform the local coordinates into normalized device coordinates or NDCs. Uh, so to designate where it actually appears on the screen. The model matrix transforms the local coordinates of the object into global coordinates. The view matrix transforms the global coordinates into coordinates from the perspective of the camera. The projection coordinates converts 3D into 2D. That is, it converts it to finally into the NDC. There are two types of projection, perspective and orthographic. We're going to be using perspective projection, where objects far away appear smaller and objects closer appear bigger. The fragment shader is much simpler. It just takes in the texture coordinates and the color values from the image and maps them onto the screen. Now we can actually focus on what's happening in runtime. First, we set the background color, then we activate our shaders. The model matrix is the matrix that maps our local model coordinates into global coordinates within the context of the scene. By transforming this matrix, we can change the cube's orientation, scale, and position. So we can use the model matrix to rotate the cube over time. OpenGL comes preloaded with functions that can do that. So we don't actually have to manually write those matrices, which makes things really simple for us. You have a rotating cube with shaman textures on it. That's fucking insane. You know what's you know what's cooler than a rotating cube? A camera. Implementing a camera is fairly straightforward. We just use the lookat function in OpenGL in conjunction with the view matrix to implement it. We can make the camera swing around, or we can even make it move around using WASD. We can add mouse control using Euler angles and make a fully fleshed first-person controller, which looks like this. Mm, now that's fucking cool. Okay, this is as far as I've come in my OpenGL journey, I guess. So I'll make a part two on lighting, materials, and stuff. Let's see. And that's about it. Thanks for watching. consider subscribing.
See ya.